Okay, so let's just go through this first one together. So we've got an equation involving some complex number z. Okay, so whenever you see a complex number, or so whenever you see z, think it's a complex number. All right. So what type of equation is this, do you think? So z to the power 4 minus 2z squared plus 4 equals 0. That looks very, very familiar to an equation which we already know. Yeah, it looks close to a quadratic. I mean, it's not quite because there's a z to the power 4 there, but hopefully you're familiar with this technique of a hidden quadratic. It basically looks like a quadratic, like that power is double that power. So let's just try making a substitution here. So let's go, for example, let t equals z to the power of 2, and then let's see what happens. So if we let t equals z to the power of 2, would you be happy that becomes t squared? Yeah? So t squared minus 2 lots of, well, z squared is t, plus 4 equals 0, okay? And then we just solve this like we would an ordinary quadratic. So let's first of all see if it will factorise. Does it factorise?
No.
Nope. Okay, so what do we go for instead? Yeah, you could do. So you could think about... okay, so you're thinking about maybe completing the square? Yeah? Yeah, you could absolutely complete the square on this. I would go with quadratic formula. Yeah, so it's the same kind of idea, actually, completing the square, and quadratic formula is the same thing. So I could go t is equal to minus b, so positive 2, plus or minus the square root of b squared,
I also think so.
minus 4 times a times c, so it's negative 16, good, all divided by 2. Okay?
Yeah.
Okay, so it would become 2 plus or minus the square root of negative 12, yeah? All divided by 2. Now, ordinarily, you'd say, there are no real solutions here because you see the square root of a negative number. But now we know about complex numbers, we can totally work with this. How could I rewrite that? That square root of negative 12.
Plus minus.
So I could write it as 2 plus or minus. Would you be happy square root of negative 12 would be the same as the square root of 12 times the square root of negative 1, or the square root of 12i? So that's what I mean by rewriting it. Yeah. And then, would you be happy that the square root of 12 would be 2 root 3? Yeah? So this would become 2 plus or minus 2 root 3, lots of I, all divided by 2. Now, just because when we write a complex number, or in this case when we write t, we tend to write it as a real part plus or minus an imaginary part. So I'm going to separate this out rather than writing over the same denominator. In other words, I'm going to write it as 2 divided by 2, which is 1, plus or minus 2 root 3 divided by 2, or just root 3i. Is that okay? Now you've got to remember, that's what t is equal to. That's what t is equal to. I don't want t, I want z squared. You okay with that? So we need to just be a little bit more careful here. So I know then that z squared has got to be equal to this. So 1 plus or minus the square root of 3 lots of I. How can I work with this then? How can I work with this? Yeah, I'd take the square root, wouldn't I? Plus or minus the square root. Okay, so let's try this. So z should be equal to plus or minus the square root of 1 plus or minus root 3 lots of I. Is that okay? Yeah. Now, of course, this doesn't really look very pretty, does it? Like, I'm writing a complex number as a square root of something. Like, this does not look very pretty. So what could I do? What could I do here? What could I do here instead? I mean, all I'm literally doing is taking the square root of a complex number. Are you happy this is exactly the same as what we were looking at last week? Yeah, just taking the square root of a complex number? So how do I do that? Yeah, good. So this is the same as taking this complex number, whatever it is, and raising it to the power of a half. Okay, so my question is, Yeah, I've effectively got 4 complex numbers here, haven't I? I've got like the positive version of square root of 1 plus root 3i and square root of 1 minus root 3i, and I've also got the negative version of that as well. So I've got 4 complex numbers. Just to illustrate my point, I'm just going to take the positive root for the time being, but you're happy you can go back and do the negative one yourself. Okay? So if I just take the positive one, so I've got either root of 1 plus root 3i, or root of 1 minus root 3i, okay? So would you be happy, like you say, this is the same as raising this complex number to the power of 1/2. Now, if I'm taking the square root of a complex number, who can remember the recipe from last week? How do we go about doing that? So what's the first thing that we need to do? What form do we need to write these complex numbers in? Good. We need to write it in either polar form or Euler form. Just basically a form which has a modulus and an argument, okay? So I guess first of all, let's find the modulus and argument of each of these complex numbers, write it in either polar and Euler form, and then you can take it from there, okay? So what would R be in this case? What would the modulus of 1 plus root 3i be? How would you calculate it? Would you be happy it's just the square root of 1 squared plus root 3 squared? So 1 squared plus root 3 squared, which comes out as 1 plus 3, which is 4, so therefore it's going to be 2. You okay with that? Because root 3 squared is just 3, isn't it? Yeah? You sure? You're looking at me strangely. I'm just squaring that bit, I don't worry about the square root for the time being because I'm just going to raise all of that to a power of 1/2 in just a second. I need to write this thing, the 1 plus root 3i, bit as a polar number first, as a polar form first. Okay, so don't worry about the square root, I'll just raise it all to the power of 1/2 in just a second. What about theta? What about my argument? Yeah, good. Tan inverse of the imaginary bit divided by the real bit. So what is the tan inverse of root 3?
60?
I think so. What's it in radians, though? Yes, exactly. Pi by 3. Yeah, good. Well done. Yeah, 60 degrees, which of course in radians will just be 180 divided by 60, so it must be pi by 3. Okay, good. Now, if I'm going to write this in a modulus argument form, what do you prefer, polar or Euler?
Euler.
Euler. Okay, fine, let's go with it. So in Euler form, what would 1 plus root 3i be?
B?
Yeah, what would you write? How would you write 1 plus root 3i in Euler form? So 1
2.
would just be 2
Yeah.
e
E.
to the
Yeah.
power of...
Pi by 3.
Perfect. Yeah, well done. Got there in the end, right?
It's easier than polar.
Yeah, exactly. Well, I mean, it's easier because it's less long, right? It's shorter. But it's still exactly the same idea. You've still got your modulus and you've still got your argument there. Okay, fine. Now, what I'm going to do is I'm going to take this and I'm going to raise this to the power of 1/2. I'm going to square root it. Okay, so I need to raise all of that to the power of 1/2. Now, would you be happy if I did this? I'd be taking the square root of 2, like 2 to the power of 1/2. E to the, well, I just multiply those together. So I get pi by 6i. You happy with that? Okay, now obviously I've just done that one for the time being. So I'll come back to this one in just a second. Okay. Now, would you be happy that that is a square root? Okay, that is my base root, if you like. But there's another one. How many roots am I expecting? I'm expecting 2, right?
Yeah.
Like if I'm taking the square root of a number, I'm expecting 2 different roots. My question is, how do I find the other root?
By taking negative.
So what's the spacing between these roots? Do you remember this? So
Spacing. You mean?
yeah, good. So let's just make sure we're okay. So I found one root, root 2 e to the pi by 6. That's going to be about there somewhere. Okay, so that's my first root. my other root is going to be over here somewhere. Because if you remember the spacing between my roots, I take 2 pi and I divide by the number of roots which I have, which in this case is 2. So the spacing between my roots has to be pi radians. Is that okay? Do you remember that? Okay, good. So all I need to do is take this and add another pi radians on, and I will find my second root. So if you like, that's Z1, that's my first root. Z2 will be what? So it'll still be the same modulus, right? It'll still be root 2, but I just add pi onto my argument. Yeah, so e to the perfect 7 pi by 6i. Those are my 2 roots for that particular one there. Okay, that particular one there. Now you just need to go back and calculate the same kind of idea with this one. Okay, so just very quickly, are you happy that the modulus isn't going to change? Because it's just going to be 1 squared plus negative root 3 all squared, square rooted, which still comes out as 2. Yeah. My argument, though, is going to change because it's now going to be the tan inverse, not of root 3 divided by 1, but negative root 3 divided by 1. So what does this one come out as, Sanjay? I mean, hopefully it should be negative pi by 3, which it is. You can think about that in terms of your tan graph, okay? It's the same kind of idea. And we're back on the internet, fantastic. Okay, fine. So in which case then, I can now write this. Let's go for Euler form as well. So I can write this now as 2 e to the power of negative pi by 3 lots of I. And I am taking the square root of that. Okay, again, so I'm raising it to the power of half. So therefore, that should be equal to square root of 2 e to the negative pi by 6 lots of I. Happy with that? Okay, so that's Z1. Z2, same kind of idea. It'll just be adding on another pi radians to this. So it'll be root 2 e to the 5 pi by 6. Do you agree with that? 5 pi by 6i. Okay? So that's one root, or that's one pair of roots, that's another pair of roots. Now just remember, I only did it for the positive one. You now need to go back and do it for the negative one. That shouldn't be too difficult. Are you happy? Because you just have to stick negatives in front of all these. Because of course, if you take this positive square root, it comes out as that. So the negative square root should come out as the negatives of these. So if I just write down up in the top right-hand corner of the page, or the board, what my 8 roots effectively are, I am going to have, positive root 2 e to the pi by 6, I. But I'm also going to have negative, if I go back and think about the negative version as well. So it'll be plus or minus that. Yeah? I'm also going to have root 2 e to the 7 pi by 6, I. But again, I could also have the negative version as well. Okay, so that's another set of roots. I could also have root 2 e to the negative pi by 6i. Okay, but I could also have the negative version as well, so plus or minus. Right. And then finally, I could also have root 2 e to the 5 pi by 6i, but I could also have the negative version as well. Is that okay? So these are my 8 roots sitting up here. These are my 8 roots sitting up there. Okay.